All right, let's do another practice problem, again from two methods. Method one we will use as with respect to the x-axis, and method two we will go with respect to the y-axis. Keep in mind that x-axis means top curve minus bottom curve, and y-axis means right curve minus left curve. Let's sketch our functions. Well, we're given, this is nice, we're given 1/2 times x squared minus 1. This is this parabola right here. And we're given the ln of x plus 1 because we couldn't do a problem without that curve. That's right here. And the x-axis. So we need to draw in a horizontal line at the x-axis. And then the other critical piece of information they gave us was this is going to be the first quadrant region because otherwise it could have been down here. So this is our region. We're going to shade in some vertical lines to show top minus bottom. And then over here on the right, we will shade in horizontal lines to evoke right minus left. So top minus bottom, this is a very interesting problem because even though the curves only intersect up over here, the top curve and the bottom curve actually change at x equals 1. And let me see if I can draw that in really well for you guys. Do you see how if I drew a vertical line in here at x equals 1, my top curve here is the natural log function, my bottom curve here is the x-axis. Whereas on the right side of this vertical line, my top curve is the natural log function and my bottom curve is the parabola. So this is a fairly tricky problem, and we have two different integrals we have to set up. The first integral is just top curve of ln of x plus 1 minus bottom curve, which is just the x-axis, and that is going to be from 0 to 1. So that's a fairly straightforward setup. The second setup, once again, is top curve of the natural log of x plus 1, but the bottom curve is going to be 1/2 times x squared minus 1 because the parabola is the bottom curve now, dx, and then my lower limit of integration here is x equals 1, and I need to be solving for this intersection point. So to solve for the intersection point, honestly, the best way to do this is to put this on your graphing calculator and find that intersection, and I'll tell you that it happens to be where x equals 1.7357. And I recommend strongly, in fact, it's kind of required, that when you integrate using an irrational number in your limit of integration, make sure that you're using the exact value, meaning go grab it from your calculator. Don't just round it during the calculation. If you round off during the middle of the calculation, your final answer will likely be a small bit off and you won't get credit for it. So don't even just put in 4 decimal places. Grab the entire problem with all of the decimal places that your calculator provides. So when I put this in my calculator, overall, I'm going to get a net signed area of 0.68048, which is just going to both round and truncate to these first 3 decimal places of 0.680. And FYI, since my third decimal place is 0, I'm allowed to just provide 2 decimal places of 0.68. All right, it's time to do right minus left. Right minus left kind of looks a little bit easier here because my right curve is the parabola and my left curve is the natural log. I don't have to write 2 different integrals here. I need one integral where my lower limit of integration is here at 0 and my upper limit of integration is at the y value of this intersection point. And I'm going to tell you this, that it is not at y equals 1, even though it looks like it to the naked eye. This is a great example of when they give you the functions, you have to go into your calculator and find that intersection point. We already know from the last part of the problem that the x value of the intersection point is approximately 1.7357, but the y value of the intersection point is approximately 1.0064. And that doesn't seem like a big difference from y equals 1, but it will get you your answer wrong if you had used y equals 1. So again, when you plug this into your calculator, you'll want to use the full value with all of its expanded decimal places for the upper limit of integration. I'm just writing 1.0064 in here for my own use. Okay, so now we need the right curve. The right curve is going to be the quadratic, but I have to write it in terms of y. So let's work on that together right now. If I were to take this function and try to figure out how to write it in terms of y, I can first multiply by 2 to get 2y equals x squared minus 1. I can then add 1 to both sides. So 2y plus 1 is x squared. And then I'm going to have to take the square root of both sides. The nice thing is I only need the positive square root because I'm only dealing with the area of, or the region or the section of the graph that has, that is to the right of the x-axis. So, or the y-axis, excuse me. So x equals typically the plus or minus square root of 2y plus 1, but in this case, for my setup, I only need the square root of 2y plus 1, just the positive side, because that's the branch we're working with. Now, of course, I need to subtract out my left-hand curve. We've already rewritten the ln of x plus 1 in terms of y, and we know that that curve is going to be e to the y minus 1. Don't forget to write these parentheses around the curve because you will need to distribute that negative sign, or make sure you type it in correctly into your calculator so your calculator distributes the negative sign. And of course I need a dy here. So everything is written in terms of y. Both of my right curve and my left curve are in terms of y. I have dy and I have limits of integration in terms of y. And once again, I'm going to get the same answer of 0.68048 when I put this on my calculator to solve.